Okay. Thank you very much. Thank you very much for the invitation. Thank you very much for the organization of the conference. So I'm going to talk about this operator formula, and I will also present, among other things, joint work with some of my former PhD students, Hans Höngesberg, Lukas Riegler, and Florian Schreier-Eigner. So that's the plan. I did not expect that Christian would talk about the operator formula also, so you would get a long introduction into the operator formula. And then I chose a few topics. I chose reciprocity, which was one of the first results I had together with Lucas. Together with Flo, we have a symmetric polynomial generalization of the operator formula, which actually generalizes Schur polynomials. Then, since we have a symmetric polynomial, we can ask for Schur expansions, and I will show you one. I will also do a B-type case, and then I will expand into symplectic characters. And in the end, I will show you some Littlewood type identities where, Schur functions in the ordinary Littlewood identity are replaced by these symmetric functions. Okay, so let me start with Gelfand-Tsetlin patterns. Gelfand-Tsetlin patterns are a combinatorial model for Schur polynomials. So what is a Gelfand-Tsetlin pattern? It's very simple. A Gelfand-Tsetlin pattern is always a triangular array. It's of the shape as you can see here. We have weak increase along this direction and along this direction for all the diagonals. And then in order to get Schur functions, we need to define a weight. So it's a weight with variable x1 up to xn. And the exponent of the xi is just the difference between the row sums of row I and row I minus 1. And if you now put in the bottom row of your Gelfand-Tsetlin patterns the partition in reverse order, and you add some zeros if the partition is not long enough, then you sum over all Gelfand-Tsetlin patterns, you get the Schur polynomial. So I've done an example here, done the example 422. And I want to compute with these Gelfand-Tsetlin patterns, I want to compute the Schur polynomial. And then you just need to list all Gelfand-Tsetlin patterns with bottom row 2, 2, 4. You need to compute the weight. So for instance, let's look at the second Gelfand-Tsetlin pattern. The x1 has an exponent, a 2, because there is a 2 in the first row. The exponent of x2 is 3 because I take the row sum of the second row and subtract the row sum of the first row, which is 2, and that's why I get the 3. And for the x3, I sum up the elements in the bottom row and subtract the sum of the elements in the second row. And if you do that, you get the Schur polynomial of the partition 4, 2, 2. So maybe you're more familiar with the combinatorial model of a Schur polynomial that uses semi-standard Young tableau. So on the right, you see a semi-standard Young tableau. That's a filling of the shape of the Schur polynomial we want to compute, such that rows are weakly increasing and columns are strictly increasing. And here I also indicate the bijection. So actually the ith row of the Gelfand-Tsetlin pattern is the shape of the entries less than or equal to I in the semi-standard Young tableau. So for instance, look at all entries less than or equal to 4 in your semi-standard Young tableau. Then what shape do you get? Well, in the first row, there are 7 entries less than or equal to 4. That's why we have a 7 at the end of the fourth row of the Gelfand-Tsetlin pattern. Then for the second row of the semi-standard Young tableau, we have 5 elements. That's why next to the 7 on the left in the fourth row, we have a 5, and that's how we get the Gelfand-Tsetlin pattern. So that's quite an easy bijection. So why do I tell you about Gelfand-Tsetlin patterns? Because as you have seen actually already in the talk of Christian, alternating sign matrices are quite easy bijection to subclass of Gelfand-Tsetlin patterns, namely those where the rows are strictly increasing and where the bottom row is 1, 2, up to n. And here I indicate the bijection. You have seen it in Christian's talk also. Yep, it's a bit, the triangle looks a bit different here, but it's really equivalent. So let me, and he also had it upside down. Okay, so let's start with the alternating sign matrix. So what you do then is you add to each entry all the entries that are in the same column and above. So to each entry, you add everything that is in the same column and above. And then if you think about it for a while, you always get a 0, 1 matrix, as you also do here, of course, with the property that in the first row, there is 1, 1. In the second row, there are 2 1s. In the third row, there are 3 1s. And then in order to go to the triangle, you record row by row the positions of the 1s. So there is a 1 in the second position of the first row, so therefore the top entry of the monotone triangle is a 2. Then for the second row, you have a 1 in the first place and in the fourth place, so that's why you have 1, 4, and that's how you get the monotone triangle. And if you think about this for a while, this will always be a Gelfand-Tsetlin pattern. And Gelfand-Tsetlin patterns with strictly increasing rows are called monotone triangles. And if you have in the bottom row the integers from 1 to n, then it's in bijection with alternating sign matrices. Okay, and the operator formula enumerates something a bit more general. So instead of the prescribed row 1, 2 up to n, I allow whatever strictly increasing sequence to you want, but it's fixed. Okay, so the bottom row of my monotone triangles is always made of the integer, always made of k1, k2 up to kn, and then this formula actually gives the number of monotone triangles with this fixed bottom row. So why is it called operator formula? Because it involves an operator. It involves quite simple operator, namely the shift operator, which shifts a variable by 1. And the way you need to apply this is you don't plug in the ki's, which are integers, immediately. You have to compute this polynomial. So you have the, this product on the right, and then you have a bunch of operators which you expand. So you get a polynomial, a Laurent polynomial in the shift operators. Actually, it's not quite true because here I take an inverse, so it's a rational function in shift operators, and you need to apply this to the product. Okay, so at first it's not clear that the inverse exists. So I do take here an inverse, but one can think about it, and it's not difficult to see that this exists. But there are other versions too. There's also one without the inverse that you can see also there. So I give some alternative formulas, so you can get rid of the inverse. And also there is a constant term formulation. So the formula below here, where you have a Laurent polynomial in the xi, and you do take the constant term. That also gives the number of monotone triangles with prescribed bottom row, and they are all easily, you can somewhat easily transform one into the other, so that's not difficult. Filippo and Bronco, I think, also have a formula which I think is equivalent to this formula. And it looks, I don't know, maybe most equivalent to the last type of formula. And then maybe let me point out one thing. So next I want to explain you somehow. I want to give you an intuition about this formula. So why did I actually start with Gelfand-Tsetlin patterns? So the product, the Ki product, actually precisely counts the number of Gelfand-Tsetlin patterns. Okay, so this product I less than j, kj minus ki plus j minus I divided by j minus I, that's the number of Gelfand-Tsetlin patterns. And this product of operator actually makes sure that we have strict increase in a sense. And I'm going to explain on the next slide why, in a sense, why this is the case. So I also want to point out that with Hans, very recently, we considered the more general case of trapezoids. So instead of triangles, we considered trapezoids like this. And of course, our first thought was, well, the formula could be of the same type, okay? So it could be that we need to take Gelfand Zetlin trapezoids and apply the same operator in order to get to guarantee row strictness. That's almost true. It's not really true. So one has to apply an additional operator, which we call the hidden operator because the operator was missing in the case of the monotone triangles. But it's almost true. Okay, so now I want to explain you why we have this operator. So I want to give you an intuition behind the operator you have seen before. So the operator in the top line was just the operator in the first formulation of the formula. So let me try to explain it to you. Again, we first start with Gelfand Zetlin patterns. And if you look at two consecutive rows in the Gelfand-Zetlin patterns, and you look locally around the Ki, then actually the pair Li minus 1 Li has to lie in the Cartesian product that you can see over there. Yeah. Yes. No, I mean that the ones that I've drawn here, no, they're not the same. Okay. So yes, so with Gelfand Zetlin patterns, the situation is quite easy. If you think you have a weak increase in this direction and you have a weak increase in this direction, then around the Ki, the situation is quite simple. And now you have to think what in addition has to hold for monotone triangles. Well, we have to guarantee that Li minus 1 is different from Li. And that can be written in this rather complicated form where this strict operator appears. And if you just do the calculation, so you apply the strict operator to this Cartesian product and write it out, you find that exactly this gives you also the condition that the Li minus 1 is different from the Li. So this is how one can think about this operator. Of course, proving is a bit of a different thing, but the reason is really, the reason why this formula is true is really lies behind such considerations. Okay. Okay, so as I said, the formula does something more general. So it computes the number of monotone triangles with a given bottom row. But of course, I also wanted to prove the ASM theorem. I also wanted to specify the Ki equal to I. And that actually was not such an easy task. Nowadays, there are several possibilities, and I just indicate one here. That was not the first possibility I found. Actually, there is yet another formulation of this operator formula. Instead of the three formulas that I've shown you before, you can also consider this expression below here, which actually involves an asymmetrizer. So what is an asymmetrizer? Well, you have a function in n variables. You sum over all permutations and you permute the elements. According to the permutation, you multiply the function with a sign, and this gives you the asymmetrizer of the function. So that explains the numerator. And since it's an asymmetric function, it's divisible by this product that you can see below, and it gives you a symmetric function. And if you specify xi equal to 1, then this gives you the number of monotone triangles if all xi's are equal to 1. So that's another formulation of the operator formula. And then you can use, for instance, this lemma here. I call it an antisymmetrizer to determinant lemma. So you can actually compute this asymmetrizer. Usually it's not easy to compute an asymmetrizer, but in this very particular case, you can see that it's actually equal to a determinant. And then you're still not done. But after some further steps in your calculation, you will finally arrive at the product formula you have seen in Christian's talk. So that's one way of proving the ASM theorem with this operator formula. I want to point out that together with Flo, we actually also have a combinatorial proof of this asymmetrizer to determinant formula. It's a bit involved. It's some pages, but it's nice since there are not many bijective proofs in this field. We thought that it's probably nice to find one such proof. And now I want to point to a talk of one of my PhD students this afternoon, Markus Reibnecker. He will actually show you a different antisymmetrizer to determinant formula. Okay, so now I've explained the operator formula. Next, I want to tell you something. What do I mean by reciprocity? Well, so the idea is actually quite simple. The idea is that, if you delete the bottom row of a monotone triangle, you still have a monotone triangle and you get a recursion. And then you just need to show that the operator formula satisfies this recursion. So that the idea is quite simple. The first proof I had was many pages long. So nowadays one can do this. I can do this in 2 or 3 pages, maybe even 2. So it's not so complicated. Okay. So now reciprocity. So what do I mean by this? Well, as I said, this operator formula gives you a polynomial. And if you have a polynomial, you can plug in any, for instance, any integers ki that you want. It doesn't have to be strictly increasing. And that's what I did together actually with my first PhD student, Lukas Riegler. And instead of plugging in increasing sequence, we plugged in n minus 1, n minus 1. So we doubled each number. And it turned out that this also gives you the number of n times n alternating sign matrices. Okay, so the evaluation of this polynomial now for a weakly decreasing sequence where you double each number also gives the number of ASMs. And then actually we even have a refined, something that corresponds to the refined enumeration of alternating sign matrices. I'm not sure whether the refined enumeration was already explained. So refined enumeration is the following. So actually in the first row, there's only 1, 1 in the alternating sign matrix because there has to be 1. Otherwise the row sum cannot be 1. And if there would be 2, then the minus 1 that is in between the column cannot sum to 1 anymore. So there's precisely 1, 1 in the first row, and you can specify, say that it's in the column I, and it turns out that if you consider the evaluation that I've shown you next, this also gives this number, this refined number of ASMs. Okay, so far this is only evaluation of some polynomials. But actually, we do also have combinatorial interpretations of this polynomial for any sequence of integers. But the way we proved, so now this is accessible for giving a combinatorial proof, right? In principle, and that's not how we did this, okay? So we did not give a combinatorial proof using this combinatorial interpretation for any sequence of KIs, but in principle, it should be possible. That's something that is open. And then we have a number of other conjectures which are not even proved in any way, so not even with a computation. So for instance, if you take also a decreasing sequence, 2n plus 1, 2n down to n, then this is up to sign equal to if you just plug in the even numbers in an increasing way. So that's not proved in no way. And then the next thing is actually funny. You take n and you take an integer between 0 and n, And then you first go up from 1, 2 up to I, and then from 1 to n, and then this turns out to be independent of I, and actually again equal to the ASM numbers. So that's open. That's actually only due to Lucas. I was not involved in this. And then the next thing is a bit of a combination of what I've shown you on the first slide and just the increasing sequence 1 up to n. Well, first you go from 1 up to I minus 1. Then you take a decreasing sequence where you double each entry, and in the end you increase again. And that's independent of I and k, and again gives the ASM numbers. And that's also open. And again, you could try to prove this with the combinatorial interpretation that we have. It's actually a signed combinatorial interpretation. It does not work. It's not a unsigned animation. There is a sign involved, but it's totally combinatorial. So in a way, one could try to prove this like this. No, I did not. I have slides at the end, which could probably do that. But there are actually several versions, and I'm not sure that the one that I show you in the end is the best, but maybe the easiest to show. Yeah. Okay. I want to point out another relation that is fulfilled by these operator polynomials, which is actually very useful for the first proof of the ASM theorem that I had. So it's a kind of rotation. So these alphas are always these operator polynomials. And if you just move the first, if you move the k1 to the end and subtract n, you actually obtain the same number up to sign. And combinatorially, it doesn't make any sense if you just consider strictly increasing sequences. But since we have the combinatorial extension, it makes both sides make combinatorial sense. The question is whether there is a combinatorial proof, because this identity is really super useful for several things. And actually, there is a combinatorial proof that I have with Matjaž. It's just very complicated. It uses the involution principle, and there could be something better, I think. Okay, so I have covered, I've given you the operator formula, I've done the reciprocity. So now I want to move to the symmetric polynomial generalization. And actually the idea is very simple. So what you see here, this asymmetrizer, this has so many variables in it. So why not making use of these variables? So what I told you before is that if I take this antisymmetrizer and divide by the Vandermonde and set all xi equal to 1, then I get the number of monotone triangles. But maybe this is also a weighted enumeration of monotone triangles. So maybe we can find some weight such that this polynomial gives you a generating function of monotone triangles. And that's almost true. And I show you this combinatorial interpretation. And it's actually quite easy. So you just need to decorate your monotone triangles. So up here, you can see an example. So if you forget about these arrows here, then this is just a monotone triangle. And now the rule is that each entry has to decorate it either with an arrow to the left, to the right, or with a double arrow. And I indicate the double arrow in my example by 2 arrows on the left and on the right. And the condition is the following. So if you have an element and there is an arrow pointing to the next element, then these entries need to be distinct. So that's the only condition. So for instance, let's look at the 2 in the last row. Then it must not be equal to the entry that is northeast of it, because there is an arrow pointing towards that entry, and that's the role of these arrows. Okay, and then we needed to introduce a weight, and it's very similar to the Schur weight that you have seen. So the black part is the Schur weight. Okay, so the xi always gets the difference of the row sums. And then you need to involve the arrows. So the U takes care of the right arrow, the V takes care of the left arrow, and the W takes care of the double arrows. And you also need to involve them somehow in the exponent of the xi. And then in order to talk about these polynomials, let's call these Robbins polynomials. And in the following, I will always denote them by R. And the parameters here are, first of all, the bottom row. So you have K1 up to Kn. Then you have the xi's, and then have the u, v, and the w that take care of these decorations. And Schur polynomials are a special case. There's actually several ways to get Schur polynomials, but one is given here. If you set v and w equal to 0, then you actually allow two types of decoration. Only one decoration is left, and you just need to subtract things from the diagonals to get Gelfand-Zetlin patterns, and that's how you get Schur polynomials. Okay. So that slide explains you how to come somehow from arrowed monotone triangles to monotone triangles again. So what do I mean by this? I take these Robbins polynomials and I evaluate them at a certain point, and my claim is that this again gives the number of monotone triangles with a fixed bottom row. So somehow we have to get rid of this decoration. And so what is the evaluation that we need to take? So we need to set u and v equal to 1, w equal to -1, and all xi's are equal to 1. And my claim is that if you do this in the Robbins polynomial, you get the number of monotone triangles with a fixed bottom row. So why is this? So take a monotone triangle, and then consider all possible decorations of these monotone triangles. So there are some entries for which there is no choice. So if an entry is equal to its northwest neighbor, then an arrow can only point in the other direction because it must not point to an element that is equal. And the same if an element is equal to its northeast neighbor, then an arrow can only point in the other direction. But if this is not the case, then all decorations are allowed. And now it's an easy calculation. Let L be the number of the first type, R be the number of the second type, and F be the number of entries where you don't have such a restriction. Then the generating function of all decorations of a fixed monotone triangle is just written down here. If in addition you specify xi equal to 1, and now you see why I chose u, v equal to 1 and w equal to -1, then u, v plus w is just equal to 1, and every monotone triangle gets weight 1. Okay, so this is how Robbins polynomials actually generalize the operator formula. And now you even have a weighted enumeration of decorated monotone triangles. And together with, so that this is all work I've done with Flo. So we actually have a formula for this generating function. So the generating function is written in terms of a asymmetrizer again, divided by the van der Waals determinant. And it's, of course, a symmetric function because you divide asymmetric polynomial by the smallest asymmetric polynomial in a sense. Yes, of course, you can also convert that to an operator formula. Okay, there is now something in addition you may have noticed. I only had a u, v, and w before, but now there is also a t. So actually what I show you here is the generating function of arrowed Gelfand-Zetlin patterns. So I was always talking about arrowed monotone triangles, but actually there's something more general. There are arrowed Gelfand-Zetlin patterns, but if you do set t is equal to 0, you really do get the generating function of arrowed monotone triangles. But I also want to answer the question, what is a arrowed Gelfand-Zetlin pattern, because that will be, Arturo will give a talk about those. So let me explain it. So an arrowed Gelfand-Zetlin pattern is a Gelfand-Zetlin pattern where in addition So it's again a decorated Gelfand-Zetlin patterns, but now you also allow that the element has no decoration. And I indicate this with the empty set. And now the rule is the following. So if you take a little triangle in your Gelfand-Zetlin pattern, and you have the situation that x is equal to y, and actually x is pointing to the y, which was previously not allowed, then also the set must be equal to x and y, and from set there must be a decoration pointing to y. Okay, so if there is one bad thing on one side, it also has to happen on the other side, and that's true also for the symmetric situation. And since this is so bad, this gets a sign. Okay, so whenever you have this bad situation, you get a sign, and what you buy from this, of course, is a signed enumeration. But the formula that I've shown you before is the signed enumeration of this arrowed Gelfand-Zetlin patterns. Below the role of the t counts, well, you see it on the next slide, the t counts the decoration, the exponent of the t is the entries that have no decoration. Okay, because that's what was added in this thing here. And at the bottom, you can see an example, and the purple triangle is one that is bad in the sense that I've explained above. Yeah?
There's no complete problem. The arrows going from what?
No, yeah. No, there's no. Okay, so this answers Christian's question. So here I give the weight. So it's very similar to what you have seen before, but I add the t, and I also need to add the sign that I've shown you before that comes from these very bad little triangles. And now I've just repeated the formula. So you have seen that's just the formula that I've shown you before already. So it's this asymmetrizer formula. And actually here you see that this is a generalization of the whole little with polynomials, which will actually play a role in Moritz's talk that will come right after my talk. Okay, so now I've introduced the symmetric functions generalizations of the operator formula. And now since we have symmetric function, we can look at some Schur expansion. So that's our next goal. In general, that's open. So if you just consider any sequence Ki, we don't have that, but we have that for very specific cases. We have that together with Flo again. We have this for the ASM case, which means that the Ki's are just the integers from 1 to n. And to be honest, we actually consider a modification, but it's not very complicated. It turns out that you can divide this Robbins polynomial by some product, and then actually consider the quotient of this Robbins polynomial and the product. And also that, I don't want to go into details, but also that is a generating function of some decorated monotone triangles, which we call down arrowed monotone triangles because the arrows are going down. But these details are not important. It's very similar to the definition that you have seen for arrowed monotone triangles. So, and here I give you the case n is equal to 3 example. So that's the Schur expansion that you get if you choose n is equal to 3. You see 5 Schur polynomials, and it's not a coincidence that this is a Catalan number. And actually for each of the totally symmetric plane partition, you have a term here. So each of the terms here corresponds to a totally symmetric plane partition. Not totally symmetric self-complementary, it's totally. It's another symmetry class. And now you might wonder whether there are Schur functions involved. So how do I compute the partition of the Schur function from a totally symmetric plane partition? Well, that's very simple. You just cut along the diagonal. You cut along the diagonal. Look at this example down here. You cut along the diagonal of the totally symmetric plane partition. You get the diagram that is on the left. And then you need to add a row in the way that I've indicated over there. And that's how you get the partition of the Schur function. So here are a bit more details. Well, first of all, I take Frobenius notation, so which means that so for the diagonals, I choose the arm and the leg lengths. This is A1, this is B1, this is B2, this is A2. So this is how you can encode the Ferrer's diagram of a partition 2 by Frobenius notation. In that way, it's actually easy. I still need to tell you what's the weight over there, this U, V, W weight. And with this Frobenius notation, that has an easy description. And then the result is that the Schur expansion is just the sum over all totally symmetric plane partitions. You take the partition given by this diagonal, which I've just described. You compute the weight, and this gives you the Schur expansion. And actually, a combinatorial proof of that is open too. Okay, so you could wonder, how can you decompose an arrowed monotone triangle in a totally symmetric plane partition and into a semi-standard Young tableau? So you need to get a pair of a totally symmetric plane partition and a semi-standard Young tableau. And you know, this identity also has a lot of weights in it. So there are n variables. So maybe the hope is bigger to find something here, because if you want to have a weight preserving bijection, you actually have a lot of informations because there are a lot of weights involved. So maybe instead of looking at Gog-Magog, maybe here you have more information. So I invite you to look at this, because that's also a connection between ASM objects and plane partitions. Okay, so there's actually a B-type result of that case, which I have with Hans. One can, of course, also consider vertically symmetric plane partitions. So these are symmetric with respect to the middle column. And if one thinks about it for a while, that actually corresponds to monotone triangles that have in the bottom row the even integers. And since it's a B-type case, we don't consider the Schur expansion. We consider the expansion into symplectic characters. And actually, the result is in perfect analogy. So we do expand with respect to the symplectic characters. And instead of totally symmetric plane partition, we have to add the symmetry. We have to add the self-complementariness. Okay, so just add this one symmetry. And you also get an expansion. And also here, I invite you, again, it has, you know, many weights involved. I invite you to find a bijection between these arrowed monotone triangles, where in the bottom row you have the even integers, and a pair of a totally symmetric self-complementary plane partition and a symplectic tableau. This is what it is in the end, because the symplectic characters are a generating function of symplectic tableau. Okay, so now I come to the last part. I come to these Littlewood type identities. So the idea is again very easy. So here I show you the ordinary Littlewood identity, which tells you that the sum of all Schur functions is just a simple product. Okay, and of course now we would like to replace the Schur polynomials by these Robbins polynomials. And this works in some cases. In some cases, one gets some nice right-hand sides. What do I mean by cases? It all depends on how we specialize these T, U, V, and W. These variables that take care of the different decoration. And the case we discovered the first was when we said T, U, V equal to 1, and the W is just a W. It doesn't need to be specialized. And it turns out that if we sum over all KIs, then we do get a rather simple product on the right-hand side. There's just something added to the numerator. And that actually appeared in the enumeration of alternating sign triangles. And now I take the opportunity to actually introduce alternating sign triangles. So that's a bit of a detour now, but I thought probably it's nice to introduce them too, and also to show some work I did together with Roger. What's a alternating sine triangle? So what has changed is that we now have a different shape. It's not anymore a square shape, but again, the entries are 0, 1, and -1. And what are the conditions? The conditions are quite similar. Again, the ones and -1s alternate in each row and each column. And again, the row sums are 1. And the only difference is with the columns. The columns do not need to sum to 1, but what we require is that the top entry of each column is actually a 1, if it exists. It doesn't have to exist. And at the bottom, you can see an example. So all these conditions are fulfilled in example. You see also that a column need not to contain a non-zero entry. For instance, the first and the last columns are examples of such. So here are all alternating sine triangles of order 3. You see that there are 7 of them. So as it is the case for alternating sine matrices, and together with Arvind and Roger, we showed that the number of alternating sine triangles is again given by the same number as alternating sine matrices. I want to show you a bit more. So of course, if you want to access a bijection, then it's good to have statistics that have the same distribution for both objects. And there is a quite easy statistic that is has this property. You just need to consider the number of -1s for alternating sine matrices and for alternating sine triangles. And maybe let's first consider the case when there is no -1, so when the statistic is equal to 0, then it's just permutation matrices in the case of ASMs. And I claim that for ASTs, it's the same number. One has to think about this for a minute or so. So let's do that. So let's enumerate alternating sine triangles without -1. Well, what is an alternating sine triangle without -1? So each row contains a unique one, and there's at most one occurrence of a 1 in each column. Again, you see an example here. And now we do the following. So we work from bottom to top. So in the bottom row, there needs to be a 1, okay, because every row needs to have a 1. Then the next row, in principle, there would be 3 possibilities, but the central column we cannot do because every column needs to have at most 1. So there are 2 choices. Then for the next row, there in principle would be 5 choices, but 2 are already taken, so 3 choices. So altogether, you get n factorial. So the proof is easy now for the case when there is no -1, but the result is true in general. So if you fix the number of -1s, you get the same number for alternating sine matrices as you get for alternating sine triangles. You can actually even add the inversion number. I'm not going through this slide. So if you even add the inversion number, you again have the same numbers if you fix the number of -1s and if you fix the inversion number. Okay, so now I come back. So actually our topic at the moment are a Littlewood identity. Yeah.
But there is darkness.
No, there's no bijection.
Oh.
So this is proven computationally again. Quite, yeah. Good luck. Okay, so actually our topic at the moment is Littlewood identities. And in this case, I also have a bounded Littlewood identity, which means that I bound the entries KI. So I bound the entries in the bottom row. At the top, you see the classical bounded identity for Schur polynomials. And at the bottom, you see the bounded identity that I get for the specialization of the parameters T, U, V equal to 1. And here's a formula. Actually, Moritz has quite a nice application of this. With this, he could show that a quite refined alternating sine triangle counting is the same as a quite refined counting of Magog. And that's actually an analog. I think that's an analog of the Gogh-Magog thing, except for this is actually proof and not a conjecture anymore. Okay, so now I want to come to this interesting sequence, which I think Philippe knows best. Well, now I take the right-hand side of this Littlewood identity, which is of course equal to the left-hand side, otherwise it's not an identity. And it turns out if you specify in that way, xi is equal to 1, w is equal to -1, m is equal to n minus 1, you get up to a power of 2 numbers that Philippe has seen in the 20 vertex model. And this sequence is actually a special case of the theorem that I've shown you next, that I will show you next. So this determinant, actually we can do a more general case. We do not need to specify m is equal to n minus 1, again together with flow. I have a theorem telling you what is this aeration. So it's this very simple product formula. And it does count these decorated Gelfand-Zetlin patterns where you restrict the bottom row by m. And now I can point to Arturo's talk. So he will show a combinatorial. Actually, now that the question is open, so on the one hand, we have these Gelfand-Zetlin patterns, this error Gelfand-Zetlin pattern. On the other hand, Philippe has the 20 vertex model. Is the combinatorial way to come from one object to the other? There is one, and what we don't have so far. So of course we want to pull the result that we have with this more general M to the 20 vertex model side, and the hope is that this bijection can actually do that in the end. So that, but we don't know yet. But that was would be the hope. But in any case, one can explain why our objects for M is equal to n minus 1 are just the 20 vertex configurations. And I'm coming to my last slides. So actually, together with Hans now again, I have another Littlewood identity. So one has to look at the details. It's always about these parameters T, U, V, and W, but W is always, we don't need to specify. In this case now, we let the T be equal to 0. So that's again the true monotone triangle case. So there's no sign involved. And this identity tells you that if you sum over all these Robbins polynomials, you do get the ordinary product that you get for the Littlewood identity and some generating function of diagonal symmetric alternating sign matrices. So this is this Littlewood identity. Actually, from work of Petrov in probability, there follows the corresponding Cauchy identity. So that also has a Cauchy identity. For the other case I've shown you, we didn't find such a thing. And in this case, again, well, you just now take the product of two such Robbins polynomials, and you get the product you always get for the Cauchy identity on the right-hand side together with some 6-vertex configuration generating function. And actually, both identities generalize the classical Schur and Littlewood identity. And right after my talk, I think after the coffee break, Moritz will give you much more details about these things and will show you some generalizations. And that's it.